Hello everyone, I'm Rebel and I'm here to present OASIS, Optimized Adaptive System for Intelligent SLAM. I'm working with Professor Danya Navard at SDSU and Professor Dutt at UCI. Let's first begin by talking about what SLAM is. It's designed to address the problem of machine perception. How do robots, drones, and autonomous systems see the world around them and figure out where they are relative to what they're seeing? It's an approach to perform sensor fusion, converting or combining sensor data to produce a map, the things we see, and a localization where we are relative to what we see. And this information is critical, especially for machines moving through environments. It needs to be done in real time, and more importantly, it needs to be done in real time and accurately to avoid causing accidents. Either you misjudge where you are and you run into a wall, or you misjudge where the wall is and you run into it. Both are problems that need to be planned for with a accurate SLAM system. And SLAM itself is also about dealing with error. Not all sensors are perfect. Some have absolute errors, some have relative errors, and these accumulate over time. SLAM is about how we deal with that as well. Imagine for a moment you're a drone, you see this scene, and you have two cameras. You know that there's some distance apart between the cameras, and you see the scene on both. The idea here is, okay, so what are some points of interest that appear in both? This process is called futurizing a scene, and we know in general corners are interesting in both images because no matter how far apart these images sensors are, we can still see corners in both of them. So now we have a featurized scene. We have two cameras seeing the scene. We have all the corners that they both commonly spot. Now we can use some properties about our camera setup to convert this 2D image into a 3D one. And we could save this into a database, and as we're moving through the world, we could keep track of all the interest points we've seen and their projections, along with where we think we were, at least separated by time, when we collected those interest points. And so on the bottom left, you can see these blue boxes. Those are those keyframes, is what they're called in OrbSlam, and then those red dots are the featurized projections of the interest points. So now you could take a collection of these, and from various key frames, you can see which interest points they observe and connect them together using edges. And what this ultimately results in is the ability to first correct for error using a loop correction. If you've seen one set of interest points from earlier in time and you see them again later in time, you can do what's called a loop correction. And you can also correct a trajectory using a common edge amongst the entire graph. And this is what's called a graph-based SLAM algorithm. And we'll be working specifically with OrbSlam 3. It's a state-of-the-art SLAM designed to work with desktop computers. What ends up happening is if you apply this to an embedded system, you get pretty poor performance. We go from the camera producing 20 frames per second to the system consuming 20 frames per second on a desktop machine. Immediately on a embedded system, you lose about 1 in every 5 frames, 20% loss. And these frames end up producing a significant amount of absolute error. So on the desktop machine, you see about a 5 centimeter error from the overall trajectory in the worst case to about 17 centimeters, 3 times more error for 1 frame out of every 5 being lost. And just for reference, the about 50 centimeters rotor span of the drone that was used to record this data. Now, how we decide to address this is observe that not all frames are made equal. Some frames take significantly longer to compute. There are many different reasons for this, but regardless, if we lose frames, we end up producing significantly more error. So our methodology is, okay, well, instead of losing the frame, could we at least take the remaining time we have and process a fraction of the frame? And we use a heuristic to dice up the frame and budget computation to the areas we believe will produce interest points that are still relevant. And we implement this as a runtime model where we figure out what the best possible approximation of the next frame will be given the budget we have, and we produce a mask that we think will contain interest points that are relevant right now and hopefully in the future as well. And we perform this computation. And here are some results. This is a bit cherry picked because this is the best one, but even though we're showing a roughly 50% improvement here, this result is averaged about 13% across the entire data set. So here is MHO2, which is Machine Hall 2 from the UROC MAV dataset. And in the brown line, you see the line, the error that occurs when you start dropping those 1 in every 5 frames. And the error spikes pretty large in areas where there's a pretty significant change in the scene. The light blue you see is what happens when you give infinite amount of time to every frame. Deadlines are not considered at all. There's still error, it's significantly lower, but this is the ideal case. And then finally, our methodology is the dark blue. The dark blue is what happens when you budget and we focus on only the areas that we believe are important. Now, especially in these spikes, you can see that we are fairly close to the normal, but sometimes we're not. And the method clearly is a significant improvement in the worst case scenarios. That's it. Thank you very much.